Imagine a star that already died. It burned through its fuel, collapsed under its own gravity, and became one of the densest objects in the universe. Now imagine two of these corpses, each barely the size of a city but carrying more mass than our sun, locked in a death spiral around each other. They orbit faster and faster, warping space and time itself, until finally they collide. And here is what nobody expects. The collision is more violent than the explosion that killed either star in the first place. It unleashes more energy in a single second than our sun will produce in its entire 10 billion year lifetime. It forges gold, platinum, and uranium. It shakes the fabric of the universe itself, and we have actually detected it happening. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that might seem obvious, but turns out to be far stranger than most people realize. Stars die. You probably already knew that. Every star that has ever existed in the universe has a lifespan. Some live for billions of years, some live for only a few million, but eventually every star runs out of fuel. It exhausts the hydrogen and helium and heavier elements in its core that have been keeping it alive, and when that happens, the star can no longer sustain the nuclear fusion reactions that have been pushing outward against gravity for its entire life. Gravity wins. The star collapses. And depending on how massive that star was when it was alive, what it leaves behind can be one of the strangest, most extreme objects in the entire universe. But here is the part that most people never think about. Death is not the end of the story. In fact, for many stars, what happens after death is far more dramatic than anything that happened during their lifetime. Because dead stars are not quiet. They are not peaceful. They are not inert chunks of matter drifting harmlessly through space. Dead stars are some of the most dangerous, most extreme, most violently compressed objects in existence. And when two of them find each other, when two stellar corpses are locked in orbit around each other and slowly spiral inward, the result is one of the most catastrophic events the universe is capable of producing. More violent than the supernova explosions that created them in the first place. More energetic than anything you could possibly imagine. But to understand what happens when dead stars collide, you first need to understand what dead stars actually are. Because not all stellar corpses are the same. There are three fundamentally different types of remnants a star can leave behind, and each one is strange in its own way. The type of remnant depends almost entirely on one thing: how massive the star was before it died. Mass is destiny in the life of a star. Let's start with the smallest and most common type of stellar remnant, the white dwarf. When a star like our sun reaches the end of its life, it does not explode. Stars like the sun are not massive enough for that. Instead, what happens is a slow, graceful process of swelling and shedding. As the star runs out of hydrogen fuel in its core, it begins fusing helium. The outer layers of the star expand enormously, and the star swells into a red giant. Our sun will do this in about 5 billion years. It will expand so much that it will likely engulf Mercury and Venus, and possibly reach the orbit of Earth. But the star cannot keep fusing heavier and heavier elements forever. A star like the sun does not have enough mass, and therefore not enough gravitational pressure in its core, to fuse elements beyond carbon and oxygen. So eventually, the outer layers drift away into space, forming a beautiful glowing shell called a planetary nebula. and what remains at the center is the exposed core, a dense, hot ball of mostly carbon and oxygen about the size of Earth. This is a white dwarf. Now, think about what this means. You are taking the core of a star that was once perhaps 1,000,000 times the volume of Earth and compressing it down into something roughly the size of our planet. The mass of the Sun, or close to it, squeezed into a volume the size of Earth. The density is almost beyond comprehension. A single teaspoon of white dwarf material would weigh about 5 tons here on Earth. If you could somehow scoop out a teaspoon of this stuff and bring it back to our planet, it would weigh roughly as much as a large elephant. And that is just a teaspoon. White dwarfs are hot when they form. Their surface temperatures can reach 50,000 degrees or more. But they are no longer generating energy through fusion. There are no nuclear reactions happening inside a white dwarf. It is essentially a cooling ember, radiating away the heat it accumulated during its billions of years as an active star. Over time, trillions of years in fact, a white dwarf will slowly cool and fade, eventually becoming what astronomers call a black dwarf, a cold, dark, dead object drifting through space, invisible to the eye. But the universe is not old enough for any black dwarfs to exist yet. Every white dwarf that has ever formed is still glowing, still radiating heat from its long dead star. So what holds a white dwarf up? If there is no fusion generating outward pressure, why doesn't the white dwarf just keep collapsing under its own gravity? The answer comes from quantum mechanics, from a principle discovered in the 1920s by the physicist Wolfgang Pauli. It is called the Pauli exclusion principle, and it says that no two electrons can occupy the same quantum state at the same time. When matter is compressed to extreme densities, the electrons inside it resist being squeezed any further. They push back, creating a pressure called electron degeneracy pressure. This pressure is what supports the white dwarf against gravity. It is not heat. It is not fusion. It is a quantum mechanical effect, a fundamental property of how electrons behave when they're packed incredibly tightly together. But this pressure has a limit. In the 1930s, an Indian astrophysicist named Subramanian Chandrasekhar calculated that electron degeneracy pressure can only support a white dwarf up to a certain mass. That mass is about 1.4 times the mass of our Sun. Beyond that, the electrons cannot push back hard enough. Gravity overwhelms them. This threshold is called the Chandrasekhar limit, and it is one of the most important numbers in all of astrophysics. Any stellar remnant that ends up below this limit can become a stable white dwarf. Anything above it cannot. It must become something else entirely. Something far more extreme. The closest known white dwarf to Earth is Sirius B, the companion star to Sirius, the brightest star in our night sky. Sirius B has about the mass of our Sun compressed into a sphere roughly the size of Earth. It orbits Sirius every 50 years. When astronomers first measured its density in the early 20th century, many refused to believe the results. The numbers seemed impossible. How could something the size of Earth have the mass of a star? But the measurements were correct. White dwarfs are real, and they are exactly as dense as the physics predicts. There are billions of white dwarfs scattered throughout the Milky Way alone. They are the most common type of stellar remnant in the universe, because most stars are not massive enough to produce anything more extreme when they die. Now, let's talk about what happens when a star is more massive, significantly more massive. Stars that begin their lives with roughly 8 to 25 times the mass of our Sun follow a very different path when they die. These stars are powerful enough to fuse heavier and heavier elements in their cores. Hydrogen fuses into helium. Helium fuses into carbon. Carbon fuses into neon, then oxygen, then silicon, and finally iron. Each stage of fusion produces energy that pushes outward against gravity. But iron is different. Iron is the end of the line. Fusing iron does not release energy. It actually absorbs energy. So when the core of a massive star fills up with iron, fusion suddenly stops. The outward pressure vanishes, and in a fraction of a second, the core collapses. What happens next is one of the most violent events in the universe. The core, which was roughly the size of Earth, collapses down to a sphere about 12 miles across in less than a second. The outer layers of the star come crashing inward, hit the incompressibly dense core, and bounce off in a catastrophic explosion called a supernova. The explosion is so powerful that for a few weeks, a single dying star can outshine an entire galaxy containing hundreds of billions of stars. The blast sends the outer layers of the star hurtling into space at speeds of tens of thousands of kilometers per second, enriching the surrounding gas with heavy elements that will eventually be recycled into new stars, new planets, and potentially new life. But the core survives. And what is left behind is something truly extraordinary. A neutron star. When the core collapses past the white dwarf stage, past the point where electron degeneracy pressure can hold it up, the electrons are forced into the protons. They combine to form neutrons. The entire core becomes a ball of neutrons packed so tightly together that they are touching. This is a neutron star, and its properties are almost beyond human comprehension. A neutron star is typically about 12 miles in diameter, roughly the width of a large city. Manhattan Island is about 13 miles long. A neutron star would fit comfortably within the boundaries of a single city. But inside that city-sized sphere is crammed roughly 1.5 to 2 times the mass of our entire Sun. All the mass of a star more massive than the Sun, compressed into a ball you could drive across in 15 minutes. The density is staggering. A single teaspoon of neutron star material would weigh roughly 4 billion tons. Not millions, billions. 4 billion tons in a volume smaller than the tip of your little finger. If you dropped a teaspoon of this material onto Earth's surface, it would punch through the crust like a bullet through tissue paper and fall straight to the core of the planet. The gravitational field at the surface of a neutron star is about 200 billion times stronger than the gravitational field at Earth's surface. If you somehow stood on the surface of a neutron star, you would be crushed instantly. Not just killed. Your atoms would be compressed. A human body on the surface of a neutron star would be flattened into a layer of matter less than 1 atom thick. The gravitational pull is so extreme that light itself is bent when it passes near a neutron star. You could actually see part of the backside of the star from the front because light curves around it. Neutron stars also spin, and many of them spin incredibly fast. When a star collapses into a neutron star, the same effect that makes an ice skater spin faster when she pulls her arms in causes the neutron star to rotate at tremendous speeds. Some neutron stars complete hundreds of rotations every single second. The fastest known neutron star spins at about 716 times per second. That means a point on its surface is moving at roughly 1/5 the speed of light. These rapidly spinning neutron stars often emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse. If one of those beams happens to sweep across Earth, we detect it as a regular pulse of radio waves. This is called a pulsar, and when they were first discovered in 1967 by the astronomer Jocelyn Bell Burnell, the signals were so regular and so precise that for a brief period, some scientists genuinely wondered if they might be signals from an extraterrestrial civilization. They were eventually nicknamed LGM-1, which stood for Little Green Men. But of course, they turned out to be neutron stars, nature producing something even stranger than alien radio transmissions. Neutron stars are held up by neutron degeneracy pressure, which is similar in concept to the electron degeneracy pressure that supports white dwarfs, but far stronger. Instead of electrons resisting compression, it is neutrons that refuse to be pushed any closer together. The strong nuclear force, one of the four fundamental forces of nature, also plays a role in supporting the star at these extreme densities. But like electron degeneracy pressure, neutron degeneracy pressure has a limit. There is a maximum mass that a neutron star can have before it too collapses. This limit is called the Tolman-Oppenheimer-Volkoff limit, and it sits somewhere around 2 to 2.5 times the mass of our Sun. The exact value is still uncertain because we do not fully understand how matter behaves at these extreme densities. The physics is literally at the edge of what we know, and if a stellar remnant exceeds this limit, if it is too massive for even neutron degeneracy pressure to hold it up, then nothing can stop the collapse. The matter keeps falling inward, compressing into a smaller and smaller volume until it crosses a threshold from which nothing can return. The remnant becomes a black hole. A black hole is what happens when gravity wins completely, when no known force in the universe can resist the inward pull. The matter collapses past every barrier, past every pressure that could potentially hold it up, and it creates a region of space where gravity is so intense that not even light can escape. The boundary of this region is called the event horizon, and it is not a physical surface. It is a mathematical boundary, a point of no return. Anything that crosses the event horizon, matter, light, information, is gone. It can never come back out. As matter falls toward the event horizon, it accelerates to enormous speeds. It heats up through friction and compression, reaching temperatures of billions of degrees. This superheated material often forms a swirling disk around the black hole, radiating intensely in X-rays before crossing the final boundary. From the perspective of a distant observer, time appears to slow for the infalling matter. It seems to freeze at the event horizon, its light stretching to ever longer wavelengths, reddening and dimming until it fades from view entirely. The object never appears to cross, it just fades away. Stellar mass black holes, the kind formed from the deaths of the most massive stars, typically have masses ranging from about 5 to a few tens of times the mass of our Sun. They are smaller than you might expect. A black hole with 10 times the Sun's mass would have an event horizon only about 37 miles across. You could fit it inside a small country, but despite their relatively small size, their gravitational influence is immense. Near the event horizon, space-time itself is warped so severely that the normal rules of physics as we experience them break down entirely. So these are the three types of stellar corpses. White dwarfs, supported by electron degeneracy pressure, roughly Earth-sized, with masses up to about 1.4 solar masses. Neutron stars, supported by neutron degeneracy pressure, roughly city-sized, with masses between about 1.4 and 2.5 solar masses. And black holes, where no pressure can resist gravity, and the matter collapses beyond our ability to describe it. Each one is extreme. Each one is dense beyond anything in normal human experience. And each one is a potential partner in one of the most violent events the universe can produce. Because here is the thing that changes everything. Stars rarely exist alone. Most stars in the universe are born in pairs, or even in groups of 3 or 4. Observations suggest that roughly half of all sun-like stars, and an even higher fraction of massive stars, are born in binary systems. 2 stars orbiting each other, bound together by gravity, circling a common center of mass for their entire lives. When one star in a binary system dies and becomes a white dwarf or a neutron star, the system does not necessarily break apart. The dead star remains in orbit with its companion. And when the second star eventually dies too, you can end up with something remarkable. 2 stellar corpses orbiting each other. A binary system made entirely of dead stars. This might sound rare, but it is not. Astronomers estimate that the Milky Way alone contains millions of binary systems made up of 2 compact objects. 2 white dwarfs orbiting each other. A white dwarf and a neutron star. 2 neutron stars locked in a gravitational embrace. Even a neutron star orbiting a black hole. These systems exist throughout our galaxy and throughout every galaxy in the observable universe. They are natural consequences of the fact that most stars are born in pairs, and most stars eventually die. And here is where the story gets dangerous. Because these binary systems are not stable forever. In fact, they cannot be stable forever. The 2 dead stars orbiting each other are doing something that slowly, inevitably, seals their fate. They are producing gravitational waves, ripples in the fabric of spacetime itself, predicted by Albert Einstein in 1915 as a consequence of his general theory of relativity. These waves carry energy away from the system, and as the system loses energy, the orbit shrinks. The 2 objects get closer together. They orbit a little faster. They lose a little more energy. They get a little closer still. This process is incredibly slow at first. For most of these binary systems, the orbit shrinks by such a tiny amount each year that it would take billions of years to notice any difference. But the process is relentless. It never stops. And as the 2 objects get closer, the rate of energy loss increases. The orbit shrinks faster. The objects spiral inward more quickly. What started as an imperceptible drift becomes an accelerating plunge. Eventually, after millions or billions of years of this slow spiral, the 2 dead stars get close enough that something catastrophic happens. They collide. They merge. And when they do, the energy released in those final moments is almost beyond description. More energy than the sun will produce in 10 billion years, released in a fraction of a second. Energy in the form of gravitational waves that shake the very structure of space-time. Energy in the form of light across the entire electromagnetic spectrum, from radio waves to gamma rays. Energy in the form of matter flung outward at significant fractions of the speed of light. The exact nature of the collision depends entirely on what kind of dead stars are involved. 2 white dwarfs merging produces a very different outcome than 2 neutron stars merging. A neutron star falling into a black hole produces something different again. Each combination has its own physics, its own violence, its own consequences, and each one tells us something profound about how the universe works. But the key thing to understand right now is this: these collisions are inevitable. Once two compact objects are locked in a binary orbit, their fate is sealed by Einstein's equations. Gravitational wave emission guarantees that the orbit will shrink. The only question is how long it takes. For some systems, the merger will happen in a few 100 million years. For others, it might take longer than the current age of the universe. But given enough time, every closed binary system of dead stars will end the same way. In collision, in merger. In an event so extreme that it reshapes our understanding of physics, chemistry, and the origin of the very atoms that make up our world. The universe is filled with ticking clocks. Pairs of stellar corpses slowly spiraling toward each other across the darkness of space. Most of them are still billions of years from contact. But some are close. Some are in the final stages of their spiral. And a few have already collided while the light from those events is still making its way toward us across the vast distances of intergalactic space. What most people do not realize is that everything about a dead star collision, the violence, the energy, the aftermath, is determined by what happens during those final moments of inspiral. The last few minutes, the last few seconds, the last few milliseconds before two of the most extreme objects in the universe make contact. And what happens in those final moments is something that until very recently, we could only predict with mathematics. We had never observed it directly. We had never confirmed that it actually happens the way our equations said it should. That changed, and when it did, it opened an entirely new way of observing the universe, a way that does not rely on light at all. But that is where this story goes next. Because before we can understand the collision itself, we need to understand the dance that leads to it. The slow, accelerating, mathematically precise spiral of two dead stars falling toward each other across the emptiness of space. A dance choreographed by gravity and witnessed for the first time not with telescopes, but with machines that can feel the universe shaking. So we now know what dead stars are and that binary systems of stellar corpses are doomed. Gravitational wave emission slowly drains energy from their orbits, pulling them closer together, accelerating the spiral. But I want you to understand something about this process, because it is not just a detail. It is the entire engine that drives everything we are going to talk about. Without the inspiral, without this slow gravitational dance, dead star collisions would never happen at all. These remnants would simply orbit each other forever, two cosmic tombstones circling in the dark for eternity. But the universe does not allow that. The very fabric of space and time guarantees that these systems will eventually destroy themselves. Let's start with gravity itself, because everything depends on it. For most of human history, we understood gravity through the lens of Isaac Newton. Newton described gravity as a force, a pull between two objects with mass. The more massive the objects and the closer they are, the stronger the pull. This worked beautifully for centuries. It explained the orbits of planets, the trajectories of cannonballs, the tides on Earth. Newtonian gravity is an astonishing achievement, and it remains accurate enough for most practical purposes even today. Engineers use it to design bridges. NASA uses it to plan spacecraft trajectories. It works, but Newton's gravity has a limitation. It treats gravity as an instantaneous force. In Newton's framework, if the sun suddenly vanished, Earth would immediately feel the loss of gravitational pull and fly off in a straight line. There would be no delay. The information about the sun's disappearance would travel infinitely fast. Newton himself was uncomfortable with this idea. He called it action at a distance and admitted he had no explanation for how it worked. But he could not solve the problem, so he left it for future generations. 3 centuries later, Albert Einstein solved it. In 1915, Einstein published his general theory of relativity, and it replaced Newton's idea of gravity as a force with something far more profound. In Einstein's framework, gravity is not a force at all. It is geometry. Massive objects do not pull on each other through some invisible rope. Instead, they warp the fabric of space-time around them. Space-time is not a fixed stage on which events play out. It is a dynamic, flexible structure that curves and bends in response to the presence of mass and energy. Objects moving through curved space-time follow the curves. A planet orbits a star not because the star is pulling it, but because the planet is following the straightest possible path through curved space-time. That path happens to be a curve because the star has warped the geometry of the space around it. This might sound abstract, but it has very real, very measurable consequences. One of those consequences is something Newton's theory never predicted: gravitational waves. Einstein realized that if massive objects warp space-time, then massive objects that accelerate, that change their motion, should create ripples in space-time. These ripples would spread outward from the source at the speed of light, like waves spreading across the surface of a pond when you drop a stone. Einstein published this prediction as part of general relativity, but even he was not sure the waves were real. For decades, physicists debated whether gravitational waves were a genuine physical phenomenon or just a mathematical artifact of the equations. Some thought they were real. Others thought they were a coordinate effect, a kind of illusion that could be removed by choosing a different mathematical framework. It took until the second half of the 20th century for the debate to be settled, and the evidence came from an extraordinary source: a pair of dead stars. In 1974, 2 American astronomers named Russell Hulse and Joseph Taylor discovered something remarkable using the Arecibo radio telescope in Puerto Rico. They found a pulsar, a rapidly spinning neutron star, emitting regular pulses of radio waves, and they noticed something unusual about it. The timing of the pulses was not perfectly regular. The pulses arrived a little early sometimes and a little late other times, in a pattern that repeated every 7 hours and 45 minutes. Hulse and Taylor realized what was happening. The pulsar was in orbit around another neutron star. The 2 dead stars were circling each other with an orbital period of just under 8 hours. As the pulsar moved toward Earth in its orbit, the pulsars arrived slightly early because the distance the radio waves had to travel was shrinking. As it moved away, the pulsars arrived slightly late. By carefully tracking these timing variations, Hulse and Taylor could map the orbit with incredible precision. This system, designated PSRB 1913+16, became one of the most important laboratories in the history of physics, because Hulse and Taylor did not just measure the orbit, they measured how the orbit was changing, and what they found matched Einstein's predictions perfectly. The orbit of the 2 neutron stars was shrinking. The 2 objects were getting closer together, not by a lot. The orbital period was decreasing by about 76 millionths of a second per year. That is an incredibly tiny change. If you measured the orbital period today and then measured it again next year, the difference would be far too small to notice in everyday life. But over decades of careful observation, the cumulative effect became unmistakable. The orbit was decaying. The two neutron stars were spiraling inward, and the rate at which they were spiraling inward matched, to extraordinary precision, the rate predicted by Einstein's general relativity for a system losing energy through gravitational wave emission. This was the first indirect confirmation that gravitational waves are real. The system was losing energy at exactly the rate it should be if it was radiating gravitational waves into space. Not a little bit off, not approximately right. The match between observation and prediction was better than 99.8%. Hulse and Taylor won the Nobel Prize in Physics in 1993 for this discovery, and their pulsar system remains one of the most precisely confirmed predictions of general relativity ever measured. But here is what makes this discovery relevant to our story. Those two neutron stars are not just slowly spiraling. They are doomed. The orbit is shrinking. The inspiral is accelerating. In roughly 300 million years, those two neutron stars will have spiraled close enough to collide and merge. What is happening right now, today, in that system, is the early stage of a process that will eventually produce one of the most violent events in the universe. The gravitational waves being emitted right now are incredibly weak. They carry away a tiny amount of energy with each orbit. But as the stars get closer, the waves get stronger. The energy loss increases. The orbit shrinks faster. The stars spiral inward more quickly. And the process feeds on itself, accelerating inexorably toward a catastrophic conclusion. This is the fundamental mechanism that drives every dead star collision in the universe. Gravitational wave emission. It is patient, it is relentless, and it is inevitable. Now, let's talk about what this inspiral actually looks like as it progresses, because the final stages of the spiral are where things become truly extreme. For most of the inspiral, nothing dramatic seems to be happening. Two compact objects are orbiting each other at a comfortable distance. Maybe they are separated by millions of kilometers. Maybe their orbital period is several hours or even days. The gravitational waves they emit are incredibly weak, carrying away only tiny amounts of energy. The orbit shrinks so slowly that you would need decades or centuries of precise measurements to detect any change at all. This phase can last for hundreds of millions or even billions of years. The two dead stars circle each other patiently, losing energy so gradually that for all practical purposes, the system appears stable. The universe has plenty of these systems scattered throughout every galaxy. Pairs of stellar corpses locked in slow orbits, ticking away like cosmic clocks, each tick bringing them imperceptibly closer to collision. But as the separation decreases, the physics changes. Gravitational wave emission depends very strongly on the distance between the two objects. The closer they are, the stronger the waves, and the stronger the waves, the faster the system loses energy. And the faster it loses energy, the closer they get. This creates a feedback loop. The inspiral accelerates. What was once imperceptible becomes measurable. What was measurable becomes dramatic. And what was dramatic becomes catastrophic. In the final million years before merger, the two objects are close enough that their orbital period has shortened significantly. They might be completing an orbit every few minutes instead of every few hours. The gravitational waves are now much stronger, carrying away far more energy per orbit. The orbit is shrinking at a rate that would be noticeable even over human timescales if we were watching closely enough. In the final few minutes, things get truly extreme. The two objects are now separated by only a few hundred kilometers. They are orbiting each other hundreds of times per second. The orbital velocity is approaching a significant fraction of the speed of light. Each object is moving at tens of thousands of kilometers per second, whipping around its partner in a blur of motion that our human senses could never follow. The gravitational waves being emitted are now enormously powerful. They're carrying away vast amounts of energy, causing the orbit to shrink visibly, measurably, in real time. If you could somehow watch the system, you would see the two objects spiraling closer and closer, orbiting faster and faster, the space between them shrinking with every revolution. In the final few seconds, the system enters what physicists call the chirp phase. The gravitational waves are increasing in both frequency and amplitude. The frequency is rising because the orbital period is shrinking. The objects are orbiting faster and faster, and the gravitational waves match that frequency. The amplitude is rising because the objects are closer together and moving faster, producing stronger waves. If you could somehow convert the gravitational waves into sound, you would hear a rising tone, getting higher and louder, faster and faster, sweeping upward like a bird's chirp. This is not a metaphor. Physicists literally call it a chirp, and it is the signature sound of two compact objects spiraling toward collision. In the final milliseconds, the objects are separated by only a few tens of kilometers. They are orbiting each other more than 1,000 times per second. The speeds are a substantial fraction of the speed of light. Space-time around the system is warped beyond anything we encounter elsewhere in the universe. The gravitational field is changing so rapidly and so intensely that the mathematics required to describe it pushes general relativity to its absolute limits. Supercomputers running for months can barely simulate what happens in these final moments. The equations become so complex, so non-linear, so intertwined, that only numerical relativity, solving Einstein's field equations on powerful computers step by step, can predict the outcome, and then contact. The two objects touch, and everything changes in an instant. But the in-spiral does not look the same for every type of binary system. The physics of the final spiral depends critically on what kind of dead stars are involved. Let me walk you through the major pairings, because the differences matter enormously for understanding what comes next. Two neutron stars spiraling toward each other produce the cleanest, most well-understood in-spiral signal. Both objects are incredibly dense and compact. Both have strong gravitational fields. Both are small enough that they can orbit very close together before making contact. This means the in-spiral lasts a long time in the detectable range. The gravitational wave signal sweeps upward in frequency over many seconds or even minutes before the final merger. This long signal is rich with information. By analyzing the shape of the gravitational wave chirp, physicists can determine the masses of the two neutron stars, how fast they're spinning, how their spins are oriented relative to the orbit, and even something about the internal structure of the neutron stars themselves. Because in the final moments before contact, tidal forces between the two neutron stars begin to deform them. They are not perfectly rigid spheres. They are made of matter, exotic ultra-dense matter, but matter nonetheless. And as they get close enough, the gravitational pull from each star begins to stretch and squeeze its partner. The amount of deformation depends on how stiff the neutron star matter is, which in turn depends on the equation of state, the relationship between pressure and density inside the star. This is one of the great unsolved problems in nuclear physics. We do not know exactly how matter behaves at densities several times higher than an atomic nucleus, but the tidal deformation of neutron stars during the final inspiral leaves an imprint on the gravitational wave signal. By measuring that imprint, we can actually constrain the equation of state. We can learn about the fundamental physics of ultra-dense matter by listening to the sound of two neutron stars falling into each other from hundreds of millions of light years away. The inspiral also generates heat, so as tidal forces deform the neutron stars, friction within the stellar material converts some of the tidal energy into heat. The surfaces of the neutron stars warm up during the final stages of the spiral. Magnetic fields get amplified. The environment around the system becomes increasingly energetic and violent even before contact. By the time the two neutron stars are about to touch, they are superheated, tidally distorted, spinning wildly, and surrounded by the most intense gravitational wave field that any object in the universe is likely to produce. Two white dwarfs spiraling towards each other follow the same basic physics, but with important differences. White dwarfs are much larger than neutron stars. A typical white dwarf is roughly the size of Earth, thousands of kilometers across rather than 12, and they are far less dense. This means that tidal effects become important much earlier in the inspiral. White dwarfs begin to deform and distort when they are still relatively far apart, because their lower density and larger size make them more susceptible to tidal forces. The gravitational waves from white dwarf binaries are also at much lower frequencies than those from neutron star binaries. Because white dwarfs are larger, they cannot orbit as close together before making contact. Their orbital periods at merger are measured in seconds rather than milliseconds. The gravitational wave frequencies are correspondingly lower, typically in the range of millihertz, far too low for ground-based detectors like LIGO to detect. Future space-based gravitational wave observatories will be needed to detect white dwarf mergers. But here's what makes white dwarf mergers especially interesting. When two white dwarfs spiral together, the less massive one usually gets disrupted first. Because it has lower surface gravity, it is easier for the companion's tidal forces to rip it apart. As the lighter white dwarf approaches its partner, it reaches what astronomers call the Roche lobe limit. This is the point at which the gravitational pull from the heavier white dwarf exceeds the lighter dwarf's own self-gravity at its surface. Material begins to stream off the lighter dwarf, flowing toward the heavier one. In some cases, this mass transfer is stable. The lighter dwarf gradually feeds material onto the heavier one, and the system evolves slowly. But in other cases, especially when the two white dwarfs are close in mass, the mass transfer is unstable. It runs away, accelerating out of control, and the lighter white dwarf is torn apart in a matter of minutes. Its material wraps around the heavier white dwarf, forming a thick, hot accretion disk. And what happens next depends entirely on the total mass of the system. If the combined mass of both white dwarfs exceeds the Chandrasekhar limit of about 1.4 solar masses, the merged object cannot remain a white dwarf. It will either collapse to form a neutron star, or, in many cases, it will explode. Carbon and oxygen in the merged material can ignite in a runaway thermonuclear detonation, and the result is one of the most important types of explosions in all of astronomy. But understanding the details of that explosion requires looking at what actually happens when the material ignites. For now, the important thing is that the inspiral of two white dwarfs follows the same gravitational wave-driven process as two neutron stars, but with different timescales, different frequencies, and a very different physical outcome at the moment of contact because the objects involved are so much larger and less dense. The third major pairing is a neutron star spiraling into a black hole, and this is perhaps the most dramatic in spiral of all, because the two objects are so fundamentally different from each other. A neutron star is matter. It has a surface. It is made of stuff, incredibly dense stuff, but real physical material that can be heated, deformed, and torn apart. A black hole is not matter in any conventional sense. It is a region of space-time so warped that nothing can escape from it. It has no surface. It has an event horizon, a mathematical boundary, but nothing you could touch or stand on. The neutron star is small and dense. The black hole might be similar in mass, but even more compact. Or it might be several times more massive than the neutron star, making the encounter profoundly unequal. During the inspiral of a neutron star and a black hole, the physics of the spiral is largely the same as for two neutron stars. Gravitational wave emission drives the orbit to shrink. The two objects circle each other faster and faster, spiraling inward. The gravitational wave signal sweeps upward in frequency and amplitude, but the ending is different. Because the fate of the neutron star depends on a critical question. Does it get torn apart before it crosses the event horizon, or does it plunge in whole? The answer depends on the mass and spin of the black hole. If the black hole is relatively low mass, say 5 to 8 times the mass of the Sun, and especially if it is spinning rapidly, then the tidal forces near the event horizon can become strong enough to rip the neutron star apart before it crosses the boundary. The neutron star reaches its Roche lobe limit, its outer layers begin to stream off, and within moments, it is shredded. Its material forms a hot accretion disk around the black hole, and some of that material is flung outward into space. This tidal disruption produces electromagnetic radiation, a potential kilonova, and ejects neutron-rich material that can form heavy elements. It is violent, bright, and astrophysically important. But if the black hole is more massive, say 15 or 20 or more times the mass of the Sun, or if it is not spinning fast enough, then the tidal forces near the event horizon are weaker. This sounds counterintuitive. A more massive black hole has a larger event horizon, and the tidal forces at a larger event horizon are actually weaker than at a smaller one. For a sufficiently massive black hole, the neutron star crosses the event horizon intact. It is swallowed whole, no disruption, no accretion disk, no ejected material, no electromagnetic signal, just a quiet disappearance as the neutron star crosses the point of no return and vanishes from the observable universe. The gravitational wave signal simply cuts off. One moment, two objects are spiraling together, producing a rising chirp of gravitational waves. The next moment, the signal stops. The neutron star is gone, absorbed entirely by the black hole. This distinction between disruption and direct swallowing is crucial because it determines whether the merger produces any observable light. If the neutron star is disrupted, there is material outside the black hole that can radiate energy. If the neutron star is swallowed whole, there is nothing. Just a slightly larger black hole and silence. The difference between a spectacular cosmic explosion and an invisible disappearance comes down to the mass ratio and the spin of the black hole. Two parameters, two numbers, and they determine whether an event is one of the brightest flashes in the universe or one of the quietest disappearances. There is one more thing to understand about the inspiral before we move to the collision itself. The gravitational waves emitted during the final spiral are not just scientifically interesting. They are powerful, enormously powerful. In the final moments before two neutron stars merge, the power radiated in gravitational waves briefly exceeds the combined light output of billions of galaxies. And for the most massive compact object mergers, when two heavy black holes spiral together and collide, the peak gravitational wave power can briefly exceed the combined light output of every star in the entire observable universe. Let that sink in. A system containing just a handful of compressed stellar remnants, each one smaller than a city, briefly radiating more power than all the stars in all the galaxies in the observable universe combined. Not in light, in gravitational waves, in ripples in the fabric of space-time itself. This is why gravitational wave detectors can detect these events from so far away. Even though the waves weaken as they spread out across the universe, their source is so powerful that by the time they reach Earth, hundreds of millions of light years from where the merger occurred, they are still detectable. Barely. The distortion they cause in space-time when they pass through Earth is almost unimaginably small. The LIGO detectors, which first directly detected gravitational waves in 2015, measured distortions in space-time smaller than 1/10,000th the diameter of a proton at peak sensitivity. That is the precision required to detect the echoes of two dead stars colliding in a galaxy hundreds of millions of light years away. It is one of the most precise measurements ever made by human beings. And those measurements tell us something profound. They tell us that the inspiral happens exactly as Einstein predicted. The gravitational waves arrive with exactly the frequency, the amplitude, and the shape that general relativity says they should have. The chirp, that rising tone sweeping upward as the orbit shrinks, matches the theoretical predictions with extraordinary precision. A theory written down by one man in 1915 using pencil and paper describes the behavior of the most extreme gravitational systems in the universe, with an accuracy that still astonishes physicists today. So this is where we stand. Two dead stars have been spiraling toward each other for millions or billions of years, driven by the invisible hand of gravitational wave emission. The orbit has shrunk from comfortable separation to violent proximity. The objects are now orbiting each other hundreds or thousands of times per second, moving at a substantial fraction of the speed of light. Space-time around them is twisted and warped beyond anything else in the universe. The gravitational wave signal is screaming, sweeping upward in frequency and amplitude, a rising chirp that encodes the masses, spins, and internal structure of the objects involved. And then the signal reaches its peak. The frequency stops rising. The amplitude surges one final time, and the two dead stars, two objects that were already the most extreme remnants of stellar death, finally make contact. What happens next depends on what they are. Two neutron stars produce one outcome. Two white dwarfs produce another. A neutron star and a black hole produce something different again. But in every case, the result is more violent, more energetic, and more consequential than the deaths that created these objects in the first place. The collision of dead stars is not an afterthought to stellar evolution. It is the crescendo, the moment when the universe takes objects that are already at the edge of known physics and pushes them beyond it. The inspiral is over, the dance is finished, And now the real violence begins. The inspiral is over. Two stellar corpses that spent millions or billions of years circling each other have finally run out of room. The gravitational wave chirp has swept upward to its peak. The two objects are separated by mere kilometers, moving at a significant fraction of the speed of light, whipping around each other more than 1,000 times per second. And now they make contact. What happens in the next fraction of a second depends entirely on what kind of dead stars are involved. And in every case, the physics is more extreme, more violent, and more consequential than almost anything else the universe is capable of producing. Let's start with the collision that has taught us the most. Two neutron stars merging. When two neutron stars finally touch, the event unfolds in stages, each one more violent than the last. The first thing that happens is not a simple crash like two solid objects smashing together. It is far more complex than that. Remember, neutron stars are not rigid spheres. They are made of matter, the densest matter in the known universe, but matter nonetheless. And in the final moments before contact, tidal forces have already begun to deform them. Each neutron star is being stretched and squeezed by the gravitational field of its partner. By the time they touch, both objects are elongated, distorted, no longer perfectly spherical. They are more like teardrops reaching toward each other. The moment of contact is catastrophic. The two deformed neutron stars slam into each other at a relative velocity that can exceed 100,000 kilometers per second. The kinetic energy involved is almost beyond description. In the first millisecond of contact, more energy is released than our sun will produce in its entire 10 billion year lifetime. The collision generates temperatures that can exceed several 100 billion degrees at the contact interface. For comparison, the core of our sun is about 15 million degrees. The center of a core collapse supernova reaches roughly 100 billion degrees at the moment the core bounces. The collision of two neutron stars surpasses even that, pushing into a regime of temperature and density found nowhere else in the modern universe. For a brief moment, the merger site becomes one of the hottest places in the entire cosmos since the Big Bang itself. But the collision does not simply annihilate both objects. Instead, the two neutron stars merge into a single, rapidly spinning object. And the nature of this remnant is one of the most important questions in modern astrophysics, because the answer determines everything that happens next. If the combined mass of the two neutron stars is below a certain threshold, the merged object can survive as a stable neutron star. It will be heavier than either of its parents, spinning extremely rapidly and intensely hot, but it will hold together. Neutron degeneracy pressure, combined with the repulsive force between neutrons at extremely short distances, is enough to support it against gravitational collapse. This new, heavier neutron star settles down over the following seconds and minutes, radiating away excess energy and gradually cooling. It might become a magnetar, a neutron star with an extraordinarily powerful magnetic field, trillions of times stronger than Earth's. Magnetars are among the most extreme objects in the universe, capable of producing flares so powerful that one detected in 2004 from a magnetar in our own galaxy briefly disturbed Earth's upper atmosphere from 50,000 light-years away. But this outcome, a stable neutron star survivor, is probably rare. In most cases, the combined mass of the two neutron stars exceeds the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can sustain. When this happens, the merged object is living on borrowed time. It forms what physicists call a hypermassive neutron star, an object that is too heavy to exist as a stable neutron star, but that temporarily supports itself through a combination of extreme rotation and thermal pressure. The merged object is spinning so fast, hundreds of times per second, that centrifugal effects provide additional support against collapse. The intense heat generated by the collision also contributes some outward pressure. These temporary supports allow the hypermassive neutron star to survive for a brief period, perhaps a few milliseconds, perhaps a few hundred milliseconds, perhaps even a few seconds. The exact survival time depends on the total mass, the spin rate, and the equation of state of ultra-dense matter, which we still do not fully understand. But these supports are not permanent. The hypermassive neutron star is radiating energy furiously. It is emitting gravitational waves, neutrinos, and electromagnetic radiation. Every form of energy it can shed, it is shedding. And as it loses energy, the temporary supports weaken. The spin slows. The thermal pressure drops. Eventually there is nothing left to hold the object up. And in a final catastrophic moment, the hypermassive neutron star collapses into a black hole. The formation of this black hole is not gentle. It happens in less than a millisecond. The matter that was barely holding itself up against gravity suddenly caves inward, crossing the event horizon and disappearing from the observable universe. But not all of the matter makes it in. The collapse is so rapid and so violent that some material on the outer edges of the remnant gets left behind. This material forms a thick, hot accretion disk around the newly born black hole. The disk contains a few percent of a solar mass worth of material, superheated to billions of degrees, swirling around the black hole at close to the speed of light. And it is this accretion disk that powers what comes next. The black hole and its accretion disk form one of nature's most efficient engines for converting matter into energy. As material in the disk spirals inward toward the black hole, it heats up. Friction between layers of the disk moving at different speeds generates enormous amounts of thermal energy. Magnetic fields become amplified to extraordinary intensities. The combined effect of intense gravity, rapid rotation, and ultra-strong magnetic fields creates something spectacular. Two narrow beams of matter and energy, called relativistic jets, are launched from the poles of the black hole. These jets shoot outward at velocities exceeding 99.9% of the speed of light, punching through the surrounding debris and erupting into space. These jets are what produce short gamma-ray bursts. A short gamma-ray burst is one of the most energetic events in the universe. It is a brief flash of gamma-ray radiation lasting typically less than 2 seconds, but carrying an almost unthinkable amount of energy. The energy released during those 2 seconds can match or exceed the total energy our sun will produce across its entire 10 billion year lifetime, all concentrated into a flash shorter than a heartbeat. The key word here is beamed. The jets are narrow. They concentrate all their energy into a tight cone. If you happen to be looking down the barrel of one of those jets from across the universe, you see an incredibly bright flash. If you're off to the side, you might see nothing at all. This beaming effect means that we only detect a small fraction of the short gamma ray bursts that actually occur. For every one we see, there are probably dozens or hundreds that are aimed in other directions, invisible to us. Short gamma ray bursts had been observed by the satellites for decades before anyone understood what caused them. For years, they were a mystery. These brief, intense flashes of gamma rays seemed to come from random directions on the sky. They were not associated with any obvious source. Various theories were proposed. Collisions between comets and neutron stars, flares from magnetars, exotic new physics. The correct answer, that they are produced by the merger of two neutron stars, or a neutron star, and a black hole, was proposed theoretically in the late 1980s and early 1990s, but it was not confirmed observationally until much later, as we will discuss. But the jets and the gamma ray burst are only part of what the merger produces. While the jets are focused along the poles, something else is happening in every other direction. The collision has flung material outward. Neutron-rich matter from the outer layers and the contact interface of the two neutron stars has been ejected in all directions. This material is incredibly hot and incredibly neutron-rich, and as it expands outward into space, cooling as it goes, something extraordinary happens inside it. The neutrons begin to assemble into heavy atomic nuclei through a process called the R process. The R process is one of the most important nuclear processes in the universe. The name stands for rapid neutron capture. Under normal conditions, building a heavy atomic nucleus is difficult. You have to add protons and neutrons one at a time, and each addition requires overcoming the electrical repulsion between protons. This is why most of the ordinary matter in the universe is hydrogen and helium, the lightest elements. Heavier elements like carbon, oxygen, and iron are built slowly inside stars through fusion reactions over millions or billions of years. But the heaviest elements, the ones beyond iron on the periodic table, require something different. They require an environment so neutron-rich that atomic nuclei can capture neutrons faster than they can decay. This is the R process, and the merger of two neutron stars provides exactly the right conditions. The material flung outward from a neutron star merger is composed almost entirely of free neutrons. As this material expands and begins to cool, those neutrons are captured by seed nuclei at a furious rate. Nuclei grow heavier and heavier, climbing up the periodic table in a matter of seconds. Strontium, barium, neodymium, platinum, gold, thorium, uranium. All of these elements and dozens more are forged in the expanding debris of a neutron star merger. The process is fast, violent, and incredibly productive. A single neutron star merger can produce several Earth masses worth of gold and platinum. Several Earth masses. That is a staggering amount. All the gold that has ever been mined on Earth, every wedding ring, every gold bar in every vault, every fleck of gold dust in every river. All of it will be a vanishingly tiny fraction of the gold produced in a single merger event. This expanding cloud of newly forged heavy elements is called a kilonova. The name is a play on the word nova, which is a Latin word meaning new star. A classical nova is a bright stellar explosion visible to the naked eye. A supernova is a supernova, a vastly more powerful version. And a kilonova is about 1,000 times brighter than a classical nova, hence the prefix kilo. Kilonovae are not as bright as supernovae, but they are still detectable across hundreds of millions of light years. And their light is distinctive. Because the ejected material is rich in heavy elements, many of which are radioactive, the decay of these radioactive nuclei heats the expanding cloud from within. The kilonova glows with a light that changes character over the course of hours and days, its color and brightness evolving as different layers of the ejector cool and as different elements dominate the emission. That evolution is a direct signature of process nucleosynthesis unfolding in real time. The visible glow of new elements being born. Now let's turn to a completely different type of collision. What happens when two white dwarfs merge? The physics here is fundamentally different because white dwarfs are fundamentally different objects. They are far less dense than neutron stars. They are far larger. And they are made of different material. While neutron stars are composed primarily of neutrons held together by the strong nuclear force, white dwarfs are composed primarily of carbon and oxygen nuclei in a degenerate electron gas. This difference in composition changes everything about what happens when they collide. As we discussed earlier, when two white dwarfs spiral together, the less massive one is usually disrupted first. Its outer layers are stripped away by tidal forces, and they wrap around the heavier companion, forming an accretion disk or a thick envelope of hot material. In many cases, the lighter white dwarf is completely torn apart and its material settles onto the surface and into the interior of the heavier one. The key question is what happens to this combined mass. If the total mass of both white dwarfs exceeds the Chandrasekhar limit of about 1.4 solar masses, the merged object cannot remain a stable white dwarf. Electron degeneracy pressure cannot support it. Something must give, and in many cases, what gives is the carbon and oxygen themselves. They ignite. Carbon and oxygen are nuclear fuel. They do not fuse under the relatively mild conditions inside a stable white dwarf because the temperature is not high enough. But the merger changes everything. The compression of the material as the combined mass exceeds the stability limit raises the temperature and density in the core to the point where carbon fusion ignites. And in a degenerate material, where pressure does not depend on temperature in the normal way, this ignition is catastrophic. In a normal gas, if fusion starts and releases energy, the gas expands and cools, regulating the reaction. But in degenerate matter, the pressure does not increase with temperature. The material does not expand. The temperature just keeps rising, which makes the fusion reactions go faster, which raises the temperature further, which accelerates the reactions even more. This is a thermonuclear runaway, an uncontrolled nuclear explosion. But the details of how this detonation starts matter enormously, because there is more than one way a white dwarf can explode. Astrophysicists have identified at least two distinct mechanisms, and which one occurs depends on the specifics of the merger. The first is called direct central ignition. In this scenario, the merger compresses the core of the heavier white dwarf so rapidly and so violently that carbon fusion ignites right at the center. The thermonuclear flame then burns outward through the entire star in a matter of seconds. This is the cleanest scenario. It produces a nearly spherically symmetric explosion and generates a consistent amount of nickel-56, which is why the resulting brightness is so uniform. This is the scenario most closely associated with the standard candle property that makes Type 1a supernovae so valuable for cosmology. The second mechanism is called double detonation, and it is more complex. In this scenario, the material stripped from the lighter white dwarf does not immediately compress the core of the heavier one. Instead, it accumulates on the surface, forming a shell of helium-rich material. This shell is volatile. As it accumulates mass and gets compressed by gravity, it eventually reaches conditions where helium fusion ignites explosively on the surface. This surface detonation sends a shockwave inward through the white dwarf. The shockwave converges toward the center, compressing the carbon-oxygen core from the outside in. When the converging shock reaches the center, it triggers a second detonation, this time of the carbon and oxygen fuel that makes up the bulk of the star. 2 detonations, one on the surface, one in the core. The surface detonation triggers the core detonation, hence the name double detonation. The double detonation mechanism is important because it can work even when the total mass of the system is slightly below the Chandrasekhar limit. The helium shell detonation provides the extra kick needed to ignite the core. This means that some Type 1a supernovae might come from systems that are less massive than previously thought. It also means that the population of Type 1a supernovae might be more diverse than astronomers assumed. Different ignition mechanisms could produce slightly different explosion energies, slightly different brightness curves, and slightly different chemical yields. Understanding these differences is an active area of research, because any variation in Type 1a brightness undermines their usefulness as standard candles for measuring cosmic distances. Now, let me paint a picture of what a kilonova from a neutron star merger would actually look like if you could observe one from a safe distance. Because the physics we have been describing produces something visually extraordinary. Imagine you're watching from a planet orbiting a star, perhaps 10 light years from the merger site. Close enough to get a spectacular view. Far enough that the radiation will not kill you. For billions of years, you have seen nothing unusual in that part of the sky. Just ordinary stars against the blackness. Then, in less than a second, a new light appears. Not gradually. Not like a sunrise. It flashes into existence almost instantaneously. In the first moments, you would see an intensely bright blue-white point of light, brighter than any star in your sky. This is the shock-heated material, the outermost layer of debris expanding at perhaps 20 to 30% of the speed of light. It is incredibly hot, hundreds of millions of degrees, and it radiates fiercely in the ultraviolet and blue visible spectrum. Over the next few hours, the light remains blue but begins to change. The fastest ejecta are expanding and cooling rapidly. Lighter R-process elements, things like strontium and zirconium, dominate the outer layers. These elements are relatively transparent, allowing the blue light to escape. The kilonova at this stage is roughly 1,000 times brighter than a classical nova, bright enough to be visible to the naked eye from 10 light years away, appearing roughly as bright as Venus appears in our sky. By the second day, the color has shifted noticeably toward red. The slower, denser ejecta deeper in the debris cloud are now dominating the emission. This inner material is loaded with lanthanides and actinides, the heaviest R process products. These elements have extraordinarily complex electron structures. Each atom has dozens of energy levels where electrons can absorb and re-emit photons. This makes the material incredibly opaque at short wavelengths. Blue and green light gets absorbed and re-emitted so many times that it is effectively trapped. Only the longer wavelength red and infrared photons can escape. The kilonova glows a deep, rich red, unlike anything else in the sky. Not the orange red of a cool star, a unique reddish hue powered by the radioactive decay of freshly minted heavy elements. Over the following days, the kilonova fades further into the infrared, becoming invisible to the naked eye by about 2 weeks after the merger. But in the infrared, sensitive telescopes could track it for months as the expanding cloud of new elements slowly dims. What you witnessed in those 2 weeks was the birth of heavy elements. You watched atoms of gold and platinum and uranium come into existence in a cloud of debris expanding at a significant fraction of the speed of light, glowing with the energy of their own radioactive decay. And then the sky returned to normal, as if nothing had happened, except that the space where two neutron stars once orbited now contains a black hole surrounded by an expanding shell of the heaviest elements in the periodic table, drifting outward into the galaxy, destined to become part of future stars and planets and possibly living things. The entire white dwarf detonates, not just the core, the entire object. In a matter of seconds, roughly one solar mass of carbon and oxygen is converted into heavier elements through explosive nuclear fusion. The explosion produces mainly nickel-56, a radioactive isotope that decays into cobalt-56 and then into iron-56. This chain of radioactive decay is what powers the light of the explosion over the following weeks and months. The explosion completely unbinds the white dwarf. Nothing is left behind. No remnant, no neutron star, no black hole. Just an expanding cloud of newly forged elements, primarily iron, silicon, sulfur, and calcium, blasting outward into space at tens of thousands of kilometers per second. This type of explosion is called a Type 1a supernova, and it is one of the most important events in all of astronomy. Type 1a supernovae are special because they are remarkably consistent. Because they all arise from the same mechanism, the thermonuclear detonation of a white dwarf at or near the Chandrasekhar limit. They all produce roughly the same amount of energy and roughly the same peak brightness. This consistency makes them incredibly useful as standard candles. Astronomers can measure how bright a Type 1a supernova appears from Earth, compare that to how bright they know it actually is, and calculate the distance. This technique has been used to measure distances to galaxies billions of light years away, and it was Type 1a supernovae that provided the first evidence in 1998 that the expansion of the universe is accelerating, driven by the mysterious force we called dark energy. That discovery won the Nobel Prize in Physics in 2011. And the tool that made it possible, the standard candle that allowed those distance measurements, was the explosion of merging white dwarfs. But not all white dwarf mergers produce Type 1a supernovae. If the combined mass is below the Chandrasekhar limit, the merger might produce a single, heavier white dwarf without detonating. The merged object would be hot and spinning rapidly, but it would settle down over time into a stable, massive white dwarf. And if the combined mass is well above the Chandrasekhar limit, the merger might instead collapse directly into a neutron star without a thermonuclear explosion. In this case, the gravitational energy released during the collapse could produce a different kind of transient, less bright than a Type 1a supernova, but still detectable. The exact boundaries between these outcomes are still being studied. The physics of white dwarf mergers is complex and depends on the masses of both dwarfs, their chemical compositions, and the dynamics of the merger itself. Finally, let's talk about what happens when a neutron star meets a black hole. This is perhaps the most dramatic and visually striking of all the merger types, because it involves an object made of matter colliding with an object that is essentially a hole in space-time. As we discussed in the Inspiral section, the fate of the neutron star depends on whether it is torn apart before crossing the event horizon or swallowed whole. Let's consider both scenarios in detail. In the disruption scenario, the neutron star approaches a relatively low mass, rapidly spinning black hole. As the neutron star gets closer, tidal forces stretch it along the direction pointing toward the black hole and squeeze it perpendicular to that direction. The neutron star elongates, becoming more and more cigar-shaped. At some point, the tidal forces exceed the neutron star's own self-gravity, and the star breaks apart. It does not shatter like glass, it tears, like taffy being pulled. A long stream of ultra-dense matter spirals outward from the disintegrating neutron star, some of it falling inward toward the black hole, and some of it being flung outward by its own angular momentum. Within milliseconds, the disrupted neutron star has formed a hot, thick accretion disk around the black hole. This disk contains anywhere from a few percent to perhaps 20 or 30% of a solar mass of neutron-rich material, depending on the mass ratio and the spin of the black hole. The rest has fallen into the black hole. The accretion disk is incredibly hot, reaching temperatures of billions of degrees. Strong magnetic fields thread through the disk, amplified by the extreme differential rotation. And just as with the neutron star merger remnant, these conditions can launch relativistic jets from the poles. A short gamma-ray burst can result, though typically less energetic than one from a double neutron star merger, because less material is left outside the black hole. The material flung outward during the disruption undergoes the same R-process nucleosynthesis as material from a neutron star merger. Heavy elements are forged as the neutron-rich debris expands and cools. A kilonova results, though its properties differ somewhat from a double neutron star kilonova. Because the geometry of the ejection is different, the kilonova from a neutron star black hole merger is often more asymmetric. More material might be flung out in the equatorial plane of the system than along the poles. The color evolution, the transition from blue to red, may proceed differently. These differences are subtle but important because they allow astronomers to potentially distinguish between double neutron star mergers and neutron star black hole mergers based on their electromagnetic signatures alone. In the direct swallowing scenario, the physics is starkly different. The neutron star approaches a more massive black hole, or one that is not spinning fast enough to produce strong tidal forces at the event horizon. The neutron star crosses the event horizon essentially intact. It vanishes. The black hole grows slightly more massive. The gravitational wave signal, which had been rising in frequency throughout the inspiral, simply stops. There is no electromagnetic counterpart, no kilonova, no gamma-ray burst, no ejected material. Just a slightly larger black hole sitting quietly in space, betraying no sign of the neutron star it just consumed. The only record of what happened is the gravitational wave signal that was emitted during the inspiral, which is now racing outward through the universe at the speed of light, carrying information about the masses and spins of the objects involved. This stark difference between disruption and swallowing illustrates something profound about the physics of compact object mergers. The outcome is not determined by the violence of the event or the amount of energy involved. It is determined by geometry, by the relationship between the size of the event horizon and the distance at which tidal forces become strong enough to disrupt the neutron star. Change the mass of the black hole by a factor of 2 or 3, and you go from a spectacular kilonova with gamma-ray bursts and heavy element production to an invisible event that produces nothing observable except gravitational waves. The universe's most extreme events are governed by precise mathematics, by the curvature of spacetime and the equations that describe it. Each of these collision types double neutron star, double white dwarf, and neutron star black hole produces a different aftermath. Different remnants, different amounts of ejected material, different electromagnetic signatures, different gravitational wave signals. The universe is not monotonous in its violence, it is creative. It uses the same basic ingredients: gravity, dense matter, and spacetime, and produces a stunning variety of outcomes depending on the specific combination. And the violence of these collisions is not just spectacle, it serves a purpose. The material ejected in these events, the heavy elements forged in our process nucleosynthesis, the energy radiated in gravitational waves and electromagnetic radiation, all of it feeds back into the universe. The heavy elements enrich the gas between stars, providing raw materials for future generations of stars and planets. The energy shapes the surrounding environment, compressing gas and triggering new episodes of star formation. The gravitational waves carry information about the merger across billions of light years, allowing civilizations like ours to detect and study events that happened in distant galaxies long before our planet even existed. The collision of two dead stars is not just a cosmic catastrophe, it is a cosmic contribution. A moment when the universe recycles its most extreme objects and produces something new, something essential. And the full scope of that contribution is what we are going to explore next. On August 17th, 2017, something happened that changed astronomy forever. At 12:41 Universal Time, the LIGO gravitational wave detectors in Louisiana and Washington State, along with the Virgo detector in Italy, picked up a signal, a chirp, a rising tone sweeping upward in frequency exactly as general relativity predicted for two compact objects spiraling together. The signal lasted about 100 seconds, far longer than any gravitational wave signal previously detected. The frequency swept upward from about 24 Hz to several hundred Hz before cutting off. The pattern was unmistakable. Two neutron stars, each roughly 1.4 times the mass of our Sun, spiraling together and merging in a galaxy roughly 130 million light years from Earth. This event was designated GW170817. The numbers encode the date, August 17th, 2017, and it was extraordinary for a reason that goes far beyond the gravitational waves themselves. Because 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst coming from the same part of the sky. A brief flash of gamma ray radiation lasting about 2 seconds. For the first time in history, astronomers had detected both gravitational waves and light from the same cosmic event. The gravitational waves told them what happened. Two neutron stars merged. The gamma ray burst confirmed the theoretical prediction that neutron star mergers produce short gamma ray bursts. Two entirely independent lines of evidence, two completely different ways of observing the universe, pointed to the same event. The same collision. The same moment of cosmic violence, 130 million light years away. But it did not stop there. Within hours, astronomers around the world were pointing their telescopes at the patch of sky where the signal came from. They were searching for the optical counterpart, the visible glow of the merger's aftermath. And they found it. In a galaxy called NGC 4993, in the constellation Hydra, a new point of light appeared where nothing had been before. This was the Kilonova, the glowing cloud of newly forged heavy elements expanding outward from the site of the merger at a significant fraction of the speed of light. The Kilonova was designated AT 2017 GFO by the International Astronomical Union and also independently catalogued as SSS 17A by the team that first spotted it with the SWOPE telescope in Chile. And it behaved exactly as theoretical models had predicted. In the first day or two, the light was blue, dominated by lighter or process elements. Then it shifted to red, then to infrared. Over the course of about 2 weeks, the Kilonova faded from view, its light dimming as the expanding debris cooled and thinned out. Spectroscopic observations, measurements of how the light was distributed across different wavelengths, reveal the chemical fingerprints of heavy elements in the debris. Strontium was clearly identified. Other R process elements were inferred from the overall shape of the spectrum and the way the light evolved over time. For the first time, astronomers were watching heavy elements being born in real time across the electromagnetic spectrum, from gamma rays to radio waves, in a galaxy 130 million light-years away. The detection of GW170817 was not just a scientific milestone, it was a revolution. It marked the birth of what astronomers call multi-messenger astronomy, the practice of observing cosmic events using multiple independent channels of information. Gravitational waves told scientists the masses of the two neutron stars and how they were spinning. Gamma rays told them about the relativistic jets launched from the merger remnant. Optical and infrared observations told them about the kilonova and the heavy elements being forged. Ultraviolet observations probed the hottest, fastest ejector. X-ray and radio observations, which appeared days and weeks later as the jets interacted with the surrounding interstellar medium, told them about the geometry and energy of the jets. Each channel provided different information. Together, they painted a picture far more complete than any single channel could provide alone. More than 70 observatories on every continent and in space participated in the follow-up observations. Thousands of astronomers contributed. The resulting papers, published in late 2017 and throughout 2018, filled entire journal issues. The scientific harvest from this single event was enormous, and all of it flowed from one thing: 2 dead stars, each barely 12 miles across, colliding in a galaxy 130 million light-years away. An event that lasted less than a second, but whose consequences will shape our understanding of the universe for decades to come. Now, let's talk about what this event taught us, because the implications run far deeper than most people realize. They reach all the way down to the atoms in your own body and the ground beneath your feet. For decades, astrophysicists had debated where the heaviest elements in the universe come from. They knew that elements up to iron are forged inside stars through nuclear fusion. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and so on, up the periodic table until you reach iron. Iron is the endpoint of stellar fusion because fusing iron does not release energy. It costs energy. So the ordinary life cycle of stars can build elements up to iron, but no further. But the universe clearly contains elements heavier than iron: gold, platinum, uranium, thorium, barium, neodymium. These elements exist on Earth. They exist in meteorites. They exist in the spectra of distant stars. Something must be making them, and that something must involve the R process, the rapid capture of neutrons by atomic nuclei in an environment so neutron-rich that nuclei can grow heavier faster than they decay. For years, The leading candidate for the R process site was core collapse supernovae, the explosions of massive stars that produce neutron stars. The idea was that the extreme conditions inside a supernova, the intense neutrino flux, the high temperatures, the rapid expansion, might provide the right environment for R process nucleosynthesis. And supernovae do produce some heavy elements, but detailed computer simulations kept running into problems. The conditions inside most supernovae turned out to be not quite right. The material was not neutron-rich enough, or the expansion was too slow, or the neutrino interactions convert too many neutrons into protons before the R process could proceed. Some heavy elements could be produced, but not enough to explain the abundances we observe in the universe. Something else was needed. Neutron star mergers were proposed as an alternative R process site as early as the 1970s and 1980s. The idea was compelling. When two neutron stars collide, they eject material that is composed almost entirely of neutrons. You could not ask for a more neutron-rich environment. The conditions are essentially perfect for the R process, and the amount of material ejected, a few percent of a solar mass per merger, is enough to account for the observed abundances of heavy elements in the universe, if mergers happen frequently enough. But for decades, this remained theoretical. No one had ever observed a neutron star merger closely enough to confirm that heavy elements were actually being produced. GW170817 changed that. The Kilonova observations showed unambiguous evidence of R process nucleosynthesis. The light curve, the way the brightness changed over time, matched models of radioactively powered ejector-rich in heavy elements. The color evolution, from blue to red to infrared, was consistent with the presence of lanthanides and actinides, the heaviest R process products. The spectroscopic detection of strontium provided direct chemical evidence. The theoretical prediction had been confirmed by observation. Current estimates suggest that this single merger event produced somewhere between 3 and 13 Earth masses of gold. Think about that number, not kilograms, not tons, Earth masses. The total mass of all the gold ever mined by humans throughout all of history is roughly 200,000 tons. That sounds like a lot, but an Earth mass is about 6 trillion kilograms. Even 3 Earth masses of gold is a quantity so vast that all the gold ever extracted from every mine on every continent across all of human civilization would be an invisible speck compared to what this one collision produced in a fraction of a second. And gold is just one element. The merger also produced platinum, iridium, osmium, palladium, and dozens of other precious and rare earth elements. It produced thorium and uranium, radioactive elements whose slow decay provides heat inside planets like Earth, driving geological activity, plate tectonics, and volcanic eruptions. It produced barium and strontium and neodymium, elements used in everything from medical imaging to electric motors, to the magnets in your headphones. This leads to a realization that is both humbling and profound. The heavy elements in our world did not come from our sun. They did not come from ordinary stellar evolution. They came from collisions like this one. Billions of years ago, before our solar system existed, neutron stars and white dwarfs collided somewhere in the Milky Way or in the dwarf galaxies that were being absorbed by the Milky Way. Those collisions ejected clouds of heavy elements into space. Those clouds mixed with the hydrogen and helium gas that filled the galaxy. And when our solar system formed 4.5 billion years ago, from a collapsing cloud of gas and dust, That cloud contained trace amounts of these heavy elements. They were swept up into the forming Earth. They sank into the planet's interior. Some remained in the crust. The gold in every ring on every finger on Earth was forged in the collision of dead stars. The uranium, whose decay heats Earth's core, driving the convection currents that generate our magnetic field, the magnetic field that shields us from the solar wind and makes life possible. That uranium was produced in a neutron star merger billions of years before Earth existed. The platinum in catalytic converters. The iridium in the thin clay layer that marks the extinction of the dinosaurs. Deposited by an asteroid that itself contained our process elements from ancient mergers. All of it traces back to moments of extreme violence between stellar corpses. You are connected to these events in a direct, physical, atomic way. The heavy elements in your body are few, but they are there. The iodine in your thyroid gland, the trace amounts of molybdenum and cobalt and selenium that your biochemistry depends on. These are our process elements. They were forged in environments where temperatures exceeded 100 billion degrees, where matter was compressed to densities exceeding that of an atomic nucleus, where the fabric of spacetime itself was being shaken by gravitational waves. And now those atoms are inside you, quietly participating in the chemistry of life, completely indifferent to the violence of their origin. Beyond heavy elements, dead star mergers contribute to the universe in other profound ways. Every merger that produces a black hole adds to the population of black holes in the universe. These black holes can then participate in future mergers. Two black holes can find each other, form a binary, and spiral together just like two neutron stars. When two black holes merge, they produce gravitational waves but no light, because there is no matter outside the event horizons to radiate. Black hole mergers are actually easier to detect with gravitational wave observatories than neutron star mergers because black holes are more massive and produce stronger gravitational wave signals. The first gravitational wave signal ever directly detected in September 2015 was from two black holes merging about 1.3 billion light-years away. Each black hole was roughly 30 times the mass of our Sun. They merged into a single black hole of about 62 solar masses. The missing mass, roughly 3 solar masses worth of energy, was radiated away as gravitational waves in a fraction of a second. 3 solar masses converted entirely into energy. By Einstein's equation relating energy and mass, that is an almost incomprehensible amount of energy. It is more energy than all the stars in the observable universe were producing at that moment combined, radiated in gravitational waves over a timescale shorter than the blink of an eye. This single event, this one merger, briefly outshone the entire observable universe, not in light, but in gravitational wave power. These detections have opened an entirely new field of astronomy. Before 2015, every observation ever made in the history of astronomy relied on electromagnetic radiation. Light. From radio waves to gamma rays, everything we knew about the universe came from photons. Now we have a second channel, gravitational waves. We can listen to the universe, not just look at it. And what we hear is the sound of dead stars colliding, the chirps and ringdowns of neutron stars and black holes merging across the cosmos. Since that first detection, the LIGO and Virgo detectors have observed dozens of merger events. Most have been black hole mergers. A few have been neutron star mergers. At least one appears to have been a neutron star merging with a black hole. Each detection provides new information. The masses of the objects involved, their spins, their distances, the properties of the merger remnant. Collectively, these observations are building up a census of compact object mergers across the universe. How often do they happen? What are the typical masses? How are the spins distributed? These questions have implications for stellar evolution, galaxy formation, and the chemical enrichment of the universe. Current estimates suggest that neutron star mergers occur in a galaxy like the Milky Way roughly once every 10,000 to 100,000 years. That might not sound like much, but the universe contains 2 trillion galaxies. Across the entire observable universe, neutron star mergers are happening constantly, several per minute, somewhere in the cosmos. Right now, as you listen to these words, neutron stars are colliding in distant galaxies, forging gold and platinum and uranium, launching jets at nearly the speed of light, shaking space-time with gravitational waves that will take millions or billions of years to reach us. White dwarf mergers are more common, perhaps once every few hundred years per galaxy. Many of these produce Type 1a supernovae. These explosions, as we discussed, are used as standard candles for measuring cosmic distances. They were the tool that revealed the accelerating expansion of the universe and the existence of dark energy. Without white dwarf mergers, we would not know that the universe's expansion is speeding up. We would not know about dark energy. One of the most profound discoveries in the history of cosmology was made possible by the collision of dead stars. Mergers also help regulate the chemical evolution of galaxies. The heavy elements produced in neutron star mergers and the iron produced in Type 1a supernovae enrich the interstellar medium. Future generations of stars form from this enriched gas. They contain higher fractions of heavy elements than previous generations. Their planets contain more iron, more silicon, more of the materials needed for rocky worlds like Earth. Over time, this chemical enrichment changes the character of a galaxy. Early galaxies, formed when the universe was young, contained almost no heavy elements. Their stars were made of nearly pure hydrogen and helium. But as generations of stars lived and died, as supernovae and mergers scattered heavy elements into the gas, later generations of stars became richer in metals. Our Sun is a relatively metal-rich star, reflecting the billions of years of chemical enrichment that preceded its formation. This means that dead star collisions are not just spectacular events, they are necessary events. Without them, the universe would be a simpler, more impoverished place. Without neutron star mergers, there would be no gold, no platinum, no uranium. Without the uranium that heats planetary interiors, rocky planets might be geologically dead. Without geological activity, there might be no magnetic fields. Without magnetic fields, atmospheres might be stripped away by stellar winds. Without atmospheres, there might be no liquid water on planetary surfaces. Without liquid water, life as we know it might be impossible. The chain of causation is long and complex, and not every link is fully understood. But the connection is real. The violence of dead star collisions billions of years ago set in motion a chain of events that ultimately made our existence possible. And there is something else. Something that might be the most profound implication of all. The gravitational waves from GW170817 arrived at Earth 1.7 seconds before the gamma rays. Both signals traveled approximately 130 million light years. The fact that they arrived within less than 2 seconds of each other, after a journey of 130 million years, confirmed something remarkable. Gravitational waves travel at the speed of light. Not approximately, not roughly. At the speed of light, to a precision of about 1 part in 1,000 trillion. This single measurement ruled out entire classes of alternative theories of gravity that had been proposed over the preceding decades. Theories that predicted gravitational waves should travel at a slightly different speed were eliminated overnight by one observation from one event. A century of theoretical debate, settled in 1.7 seconds. This is the power of multi-messenger astronomy. By combining different channels of observation, gravitational waves, gamma rays, optical light, infrared, X-rays, radio, scientists can learn things that no single channel could reveal. They can measure things with a precision that no single observation could achieve. And it all flows from events that happen in fractions of a second, in galaxies millions or billions of light years away, when dead stars finally collide. So let me bring everything together. We started this journey with a question. What really happens when two dead stars collide? And now we have the answer, or at least as much of the answer as current science can provide. Dead stars come in 3 varieties: white dwarfs, neutron stars, and black holes. Each one is the compressed remnant of a star that has exhausted its fuel and collapsed. Each one is extreme in its own way, dense, compact, gravitationally powerful, and many of them exist in binary systems, paired with another dead star, orbiting a common center of mass. These binary systems are doomed. Gravitational wave emission steadily drains energy from the orbit, pulling the two objects closer together over millions or billions of years. The inspiral accelerates. The orbital speeds increase, and eventually the two dead stars make contact. What happens at contact depends on what they are. Two neutron stars collide and merge, potentially forming a hypermassive neutron star that collapses into a black hole within milliseconds. The collision launches relativistic jets, produces a short gamma-ray burst, and ejects neutron-rich material that undergoes R-process nucleosynthesis, forging elements heavier than iron. The expanding cloud of new elements glows as a kilonova, visible across hundreds of millions of light years. Two white dwarfs can merge and detonate in a Type 1a supernova, a thermonuclear explosion that completely unbinds the star and produces mainly iron group elements. A neutron star falling into a black hole might be tidally disrupted, producing a kilonova and gamma-ray burst, or it might be swallowed whole, producing nothing but gravitational waves and a slightly larger black hole. Each of these events is violent beyond anything in ordinary human experience. Each one releases more energy in seconds than our sun will produce in billions of years. And each one matters. Because the elements forged in these collisions, the gold and platinum and uranium and thorium, are scattered into space and eventually incorporated into new stars, new planets, and ultimately into living things. The heavy elements in your body were created in events like these. Not in our sun, not in ordinary stellar processes. In the collisions of dead stars, in moments of extreme violence that occurred billions of years before you were born, in places that no longer exist, around stars that have long since faded. But this connection between dead star collisions and the atoms inside you is not abstract. It has a timeline, a chronology that stretches across most of the Milky Way's history. The Milky Way began forming roughly 13 billion years ago, not long after the Big Bang itself. The first generation of stars contained almost no heavy elements at all. They were made of nearly pure hydrogen and helium, the only elements produced in the Big Bang. These stars lived fast. Many of them were massive and they died fast. Some exploded as supernovae, producing elements up to iron and scattering them into the surrounding gas. Some left behind neutron stars, and some of those neutron stars ended up in binary systems, destined to spiral together and collide. The first neutron star mergers in our galaxy probably occurred within the first billion years or so. These early mergers were the first major sources of our process elements in the Milky Way. The gold and platinum they produced mixed with the interstellar gas, enriching it slightly. The next generation of stars formed from this enriched gas. They contained trace amounts of heavy elements that the first generation lacked. When those second generation stars died, some of them also left behind neutron stars. More mergers followed. More heavy elements were forged and scattered into the gas. This cycle repeated over billions of years. Each generation of stars formed from gas that was slightly richer in heavy elements than the generation before. The enrichment was slow and uneven. Some regions of the galaxy received more merger debris than others, depending on where and when mergers occurred. Computer simulations of galactic chemical evolution show that it took several billion years of this gradual enrichment before the interstellar medium reached the level of heavy element abundance that we observe in our solar system today. Our Sun formed about 4.5 billion years ago, roughly 9 billion years after the Milky Way began assembling. By that time, the gas cloud from which our solar system condensed had been enriched by thousands of supernovae and perhaps dozens or hundreds of neutron star mergers spread across billions of years of galactic history. The heavy elements in that cloud represented the accumulated contributions of many events, not a single explosion, but a long chain of stellar deaths and collisions, stretching back to the earliest epochs of the galaxy. Every R-process atom in our solar system carries a history. Some of those atoms might have been forged in mergers that occurred 12 billion years ago in small dwarf galaxies that were later absorbed by the Milky Way. Others might have been produced more recently, perhaps only 5 or 6 billion years ago, in mergers within the Milky Way's disk. The gold in your ring is not from a single event. It is a blend, an accumulation, a chemical memory of the Milky Way's entire violent history written in atoms. The gold in your ring was forged when two neutron stars tore each other apart in a collision so violent it shook the fabric of space-time. The uranium whose slow decay warms Earth's interior, keeping our planet geologically alive, was created in the same kind of event, perhaps in a different galaxy, perhaps in a dwarf galaxy that was later consumed by the Milky Way. The iodine in your thyroid, the selenium in your enzymes, the trace heavy elements that your biology depends on, all of them trace their origin to collisions between the densest, most extreme objects in the universe. You are not merely a witness to these events. You are a product of them. Every heavy atom in your body is a fossil, a relic of an ancient cataclysm, a piece of debris from a collision that happened so long ago and so far away that the light from it reached Earth and faded billions of years before any human eye existed to see it. And yet, those atoms survived. They drifted through space. They were swept up into a forming solar system. They became part of a planet. They became part of you. The next time you hold a gold ring in your hand, or see platinum jewelry in a shop window, or read about uranium fuel in a power plant, remember where those atoms came from. Not from a mine, not from a factory, from the collision of dead stars, from a moment when two objects, each barely the size of a city but heavier than our sun, spiraled together at a significant fraction of the speed of light and shattered each other in a burst of energy that outshone an entire galaxy. That violence, that destruction, that unimaginable force is the reason those atoms exist. And by extension, it is part of the reason you exist. The universe builds through destruction. It creates through violence. The most beautiful and precious things in our world, the elements we treasure most, were born in the most extreme environments imaginable. There is something deeply poetic about that. The gold in a wedding ring, a symbol of love and permanence, was forged in a moment of cosmic annihilation. The very atoms that we use to symbolize things that endure were created in events that lasted less than a second. And we have only just begun to understand these events. The first direct detection of gravitational waves happened barely a decade ago. The first multi-messenger observation of a neutron star merger happened in 2017. We are in the earliest days of a new era of astronomy. Future detectors will be more sensitive. They will detect more mergers from greater distances with greater precision. We will learn more about the physics of ultra-dense matter, the origin of heavy elements, the behavior of space-time under the most extreme conditions, and the population of compact objects throughout the universe. Every new detection will add to our understanding. Every new merger will teach us something. The next generation of gravitational wave detectors will transform what we can observe. The current LIGO and Virgo detectors are remarkable instruments, but they have limitations. They can detect neutron star mergers out to about 600 million light years. That sounds enormous, and it is. But the observable universe is 93 billion light years across. We are currently listening to only a tiny fraction of the cosmos. The Einstein telescope, planned for construction in Europe, and Cosmic Explorer, proposed for the United States, are next generation ground-based detectors that will be roughly 10 times more sensitive than current instruments. Because gravitational wave amplitude falls off linearly with distance, a 10-fold improvement in sensitivity means they can see roughly 10 times farther. And because volume scales with a cube of distance, that translates to roughly 1,000-fold increase in the volume of space they can survey. These detectors will be able to observe neutron star mergers across most of the observable universe. They will detect not a handful of mergers per year, but hundreds or thousands. But there is another frontier that is equally exciting. A space-based gravitational wave observatory called LISA, which stands for the Laser Interferometer Space Antenna, is planned for launch in the mid-2030s. LISA will consist of 3 spacecraft flying in a triangular formation, separated by 2.5 million kilometers, trailing Earth in its orbit around the Sun. LISA will detect gravitational waves at much lower frequencies than ground-based detectors. And at those low frequencies, the universe is rich with sources. LISA will be able to detect white dwarf binary systems throughout the Milky Way, not just when they merge, but years or decades or even centuries before they merge. Thousands of white dwarf binaries in our galaxy are radiating gravitational waves at frequencies LISA can detect. For the first time, we will be able to identify these systems, measure their orbital parameters, and predict when they will merge. We will know, years in advance, when and roughly where a Type 1a supernova or a white dwarf merger is going to occur. Imagine receiving a notification that 2 white dwarfs in a particular part of the sky are going to collide in 3 years. Astronomers could point every telescope available at that location and watch the event unfold from the very first moment. The scientific return would be extraordinary. LISA will also detect the inspirals of neutron stars and stellar mass black holes long before they enter the frequency range of ground-based detectors. A neutron star binary that is still years from merging will be emitting gravitational waves at millihertz frequencies, right in LISA's sweet spot. LISA could alert ground-based detectors and electromagnetic telescopes to watch for the final merger, enabling multi-messenger observations that are planned rather than reactive. The era of gravitational wave astronomy is just beginning. What we have seen so far is a preview, a glimpse through a narrow window. The next generation of detectors will throw that window wide open, and every heavy element forged in those mergers will eventually make its way into new stars, new planets, and perhaps new living things. The cycle continues. Stars are born from gas enriched by the deaths and collisions of previous stars. They live, they die, they leave behind remnants. Those remnants collide, forging new elements, enriching the gas again. Generation after generation, the universe grows richer and more complex, and somewhere in that cycle, on a small rocky planet orbiting an ordinary star in a spiral galaxy that is one among trillions, atoms forged in the collisions of dead stars assemble themselves into molecules, then into cells, then into organisms, and eventually into beings capable of looking up at the sky and wondering where they came from. Now you know